And entropy is represented with a symbol of a capital S. And entropy in the realms of science, it represents the amount of chaos or randomness in a system. So entropy is the amount of chaos or randomness in a system. So as the entropy increases, that means that the system becomes more random. So we see an increase in the randomness or chaos. And what that does is it increases the stability. So if you think about a system and if it has to maintain a perfect order, that's a lot of stress. So it increases the stability because it lessens the stress. So a little bit of chaos or randomness decreases the amount of stress. So the system has greater stability. So let's take a look at entropy during phase changes. And I want to start with particle diagrams. So when we draw a particle diagram where the molecules are touching and being held in an order, you should recognize that that represents our sample in the solid state. Now, the most opposite particle diagram of a solid would be one where our particles, they don't touch, there's space between them, and that represents our sample in the gas phase. And then, of course, the liquid is the phase between solid and gas, where we show our particles relatively close, but there's no order, and it gives the idea that the particles are flowing within the sample. So when a sample starts off as a solid, in order for it to change to a liquid, it has to gain heat. Heat has to enter the sample. And once when it's a liquid, in order for it to transition into the gas, the liquid must gain even more heat. So the energy transfer that requires a sample to absorb heat we use that fancy word to represent it as an endothermic process. So an endothermic process. So when you compare the temperature of the solid to the temperature of the liquid to the temperature of the gas, we would expect there to be an increase in the temperature. And temperature represents that kinetic nature or the movement of the particle. So as we see an increase in the temperature, we expect to see an increase in particle movement. Now, when you take a look at these particle diagrams from a solid to a liquid to a gas, you should notice that there is an increase in the distance between the particles. They're able to start to move away from each other. And that's a result of a change in their intermolecular attraction or the stickiness between the molecules or particles. So as we see a decrease in the attraction strength, then the particles are able to start moving away from each other. So with more particle movement and greater distance between the particles, we see an increase in the system's randomness, so we see an increase in the entropy. So if you understand those changes or comparisons going from solid to liquid to gas, you need to be able to do this in the reverse order also. So starting off with a particle diagram that represents a gas and moving all the way through a phase change where it ends up as a solid and hitting the liquid phase as between those two. So to go in the reverse process, that means that our sample had to get rid of or release heat. And so when our sample is releasing heat, we refer to that as an exothermic process because it's exiting our sample. And so when you compare the temperature of the sample as a gas to a liquid to a solid in this direction, we expect to see a decrease in the temperature And as a result, we see a decrease in the kinetic nature of the sample, so we see a decrease in particle movement. And when you look at those particle diagrams, you notice from a gas to a liquid to a solid, we see a decrease in the distance between those particles. And as a result, because they're moving closer together, their attractions are increasing. They want to stick. Their stickiness to each other becomes stronger and stronger. So we see no order, touching, maybe not order, but touching, now touching and order. We see a decrease in the randomness or chaos of the system. So we see a decrease in the entropy. Now, be able to define entropy, but also be able to look at some simple systems and identify if the entropy has changed or has not been affected. So in this process, the first thing that I want you to look at is to pay attention to the phases in the system. So on the reactant left side of this system, we start off with a sample that is in the solid state. And even though there are two products on the right-hand side, one of the products is in the gas phase. So started off with everything solid state order, and we ended up with something in the gas state. So gas has more, a gas phase has more entropy than a solid. So overall, in this system, the entropy increases. Now, number 2, take a look at this. So if you take a look here, you notice that every sample, whether it's a reactant or product, they are all in the same phase. So we can't really compare phases here for this. So number 2, if everything's in the same phase, then we're going to look at the number of moles of gas. Now, what represents the moles? Well, that's those coefficient numbers to the left-hand side. So that represents our number of moles. So here in this problem, we have 2 moles of hydrogen and 1 mole of oxygen. So on the left side, we have 3 moles of gas, and on the product side, we have only 2 moles of gas. So the more gas molecules you have, the more entropy. So because there's 3 moles of gas on the left-hand side, this side would have more entropy. And on the right side, because there's only 2 moles of gas, it has less entropy. So as you move left to right, we see a decrease in the entropy. And now our last scenario that we might come across in our class, if you take a look at all of the substances present, they are all in the gas phase, so they're all in the same phase. When you take a look on the left-hand side, we have 2 moles of gas, and on the right-hand side, we have 2 moles of gas. So they're all in the same phase. They have equal number moles of gas. So in this case, we would say for the entropy at our level, there is no change or it remains the same. So practice those ideas.